It's a pleasure to introduce Eric Lutz from Stuttgart, who's going to talk about measurement-induced quantum synchronization. Please, Eric.
So thank you very much. Can you hear me at the very end? So I would like to talk about synchronization in the quantum regime. And if you wish, this is a follow-up to Sai's presentation last week. So the talk is going to be divided into three main parts. I will first give a general introduction to classical synchronization, and then move to quantum synchronizations in two different forms. First, classical noise-induced quantum synchronization. And the second one is quantum noise-induced, meaning measurement-induced quantum synchronization. So the very first observation of synchronization in physics, at least, goes back to Huygens, 1665. And you probably all know Huygens as a great physicist, but he was also a great clock maker. Actually, the pendulum clock was first built by Huygens in 1656 with a tremendous increase in accuracy from 15 minutes a day before to 15 seconds a day after Huygens. So this made a huge difference. You could actually start relying on clocks. So what you see here is actually an original drawing by Huygens. So two of his clocks suspended on a beam on two chairs. And it just happened that Huygens was sick one day in bed, and he had nothing else to do than to observe these two clocks. And what he realized is that they would oscillate in sync, and more precisely, they would oscillate in antiphase. And this is the very first observation or first report of synchronization in the scientific physical sense, and he called that the sympathy of two clocks. So to give you a more modern definition of synchronization today, one could say that synchronization occurs in coupled nonlinear oscillators that swing in unison. And there are different types of synchronization, phase synchronization, frequency synchronization, and it occurs almost everywhere. As soon as you have oscillations that are coupled and nonlinear, you're going to have synchronization. And just to give you some very intuitive examples, just consider an orchestra and have a look at these violin players. So they're going to be synchronized by the conductor. And if they are well synchronized, you actually hear it. Because if they play in sync, you hear harmony, it's harmonious. Once they start to play out of sync, it's going to be a cacophony. So you actually hear synchronization in that context. To give you a more physical example, let me show you a small movie of coupled oscillators. So these are 5 metronomes. They are coupled by this moving beam, and start by looking at these two on the right, because very quickly they're going to move in sync. And they do it already now. The two in the middle do something else, but after a while, these two are going to be synchronized as well now. So these two are synchronized, these two are synchronized. And if you wait a little bit longer, the 4 of them are going to oscillate in sync. I think almost right now. The only one doing something different is the last one on the left. Wait a little bit longer. I think now all 5 of them move in unison. That's a nice example of classical synchronization. Now they are. I'm going to wait until the very end. It's going to stop in a few seconds. Here we are. So that's a physical example, but let me give you now some technological example by looking at some telecom network. Actually, each time you use your mobile phone, or each time we use our mobile phones, we use this kind of communication networks, and they need to be synchronized, well synchronized. And the reason for that is that they all rely on multiplexing. That's a very powerful technique to use one channel and transmit many different signals with many different frequencies. And this only works if all the switches are very well synchronized. Once this is not the case, you notice immediately because you start losing data. So in that very concrete application, synchronization, classical synchronization is very, very important. Now the question you can ask is, you need to couple these oscillators to be synchronized. How strong should they be coupled? And this is a diagram that explains how this looks like. So to make life simple, just take 2 oscillators. And let's assume that they have the same frequency at the beginning. So if they have the same frequency, you don't have to do anything. They're synchronized by definition. They have the same frequency. So you don't need to couple them. But the larger the tuning, intuitively clear is that you have to increase the coupling. So the larger the detuning, the stronger you have to couple them to still achieve synchronization. And because this diagram, I mean, this is an existence, a stability, robustness diagram, you call it the way you wish, but it looks like a tongue if you have lots of imagination. And that's the reason why people refer to that as the Arnold tongue, going back to Arnold, 1961. Now let me come back to my orchestra. Let me talk about noise. Noise is everywhere. In most cases, noise is bad in the sense that it's a disturbance. It makes everything worse. To take the example of this violin plays, again, just assume you take one of these violins and you apply a huge amount of noise on it. It's not going to be nice to hear. So this is going to degrade your signal. However, there are some cases when noise can be good. People talk about the constructive role of noise. And quite surprisingly, 1984, Pikowski made the prediction that synchronization can actually be generated by noise, not by any coupling. You just apply noise and you expect everything to become worse, and suddenly they start oscillating in sync. So that's what people call classical noise-induced synchronization. One example that I like very much, from engineering now to biology, let's consider two neurons, and when they are coupled in your brain, for instance, via a synapse, then they're going to fire in sync. So this direct coupling is going to synchronize them. But now you could torture some poor animals, take neurons off them, paddlefish neurons, you don't couple them, and then you observe them. That's a nice experiment published more than 20 years ago. That's neuron number 1, that's neuron number 2, and you realize that they spike more or less, fire more or less independently of each other. And then at some point, at time t, you start applying some noise, and you don't have to look these two diagrams, to these two plots very carefully to realize suddenly they start firing in sync. So that's a very nice example of noise-induced classical synchronization. And then by looking at the literature, I found this very nice PRX a few years ago, where they try to argue that actually noise-induced synchronization is very, very, very important in your brain. It's important for memory, it's important for attention, and it's important for sleep. I mean, we are all at 37 degrees Celsius, so we are in a thermal environment that fluctuates a lot. There is thermal noise everywhere. So it's kind of not too surprising that nature used noise for some useful purposes. And what they try to argue here, I mean, no, that's not an argument. The observation is for people having Alzheimer's, this is related to a lower synchronization as it should be. People having Parkinson's disease, it's a higher synchronization than expected for motor circuits. So they try to, it's a theoretical study, and the conclusion of that is by applying some deep brain simulation, trying to bring down the synchronization level back to normal. This would be a nice way, or useful way, to control Parkinson's or treat Parkinson's disease. So all this is classical, and this is the end of my first talk, a kind of general introduction to classical and classical noise-induced synchronization. And now I would like to move to the quantum regime and play with the noise as well. So quantum synchronization is a kind of, let's call it an emergent field. People started in earnest about 10 to 15 years ago. And once you look at the problem more closely, you realize, okay, it faces a number of serious issues. The first one being that there is no well-defined phase operator in quantum mechanics. So many people doing quantum optics in this audience, so they know that people have tried to define phase operators for a very long time, like Barnett and all the others. But this is if you want to have oscillations in phase, and you are not able to properly define a phase operator, this is slightly difficult, or make life more difficult. The Schrödinger equation gives you a linear time evolution, even if the potential is nonlinear. So having a nonlinear time evolution, as in classical mechanics, is difficult. It's a problem which is also faced by the theory of quantum chaos, for example. And as a result, so far, there is no universal theory of phase quantum synchronization yet. Talking now about noise-induced quantum synchronization, it makes life even more complicated, because if noise is a disturbance, a nuisance in classical physics, it's even more dramatic in quantum physics, because you all know that quantum properties, coherence, entanglement, whatever, are very fragile, and as soon as you apply some noise, you're going to decree everything, and then the quantumness is gone. But nevertheless, that's the topic of my talk. noise-induced quantum synchronization. So the first thing we have to do is kind of come up with an observation, a definition of synchronization. That's the one I'm going to use has been put forward by Yaksh in his group, and 2 years ago. And just take two observables, consider the expectation values, and if they become equal after some transient, then they're synchronized. The example I'm going to use is two spins, and if they do this, like the metronomes I showed you before, we call that synchronization. And of course, they shouldn't be flat, right? Because this is true if the two are equal to 0 and constant, this is not any synchronization. So to make things concrete, let's take one particular model, an XY chains of n spins, put them in an external transverse magnetic field, and we're going to apply some noise, Gaussian white noise, at a single site somewhere along the chain. And then together with one of my PhD students, Finn, we sat down and derived a condition for achieving stable synchronization in this quantum system. And what comes out is, well, first it exists, which is not completely obvious. And the second one, the condition for having stable synchronization in the system looks pretty simple. The number of spins in the chain n should be 5 plus a multiple, m times 3, and m is an integer, and u should be 3 times an integer. I'm going to come back to how to get that in a second. After a few slides, I need to provide some more information, but the most important thing here is to realize that this system is kind of boring in the sense that it's exactly solvable. You do some Jordan-Wigner transformation, and then you have it immediately. But the nice prediction is that you can have stable synchronization in this quantum system, in particular of the n spins, of the h spins. And this is what I'm going to show you. No boundary condition, it's just a chain. We don't close it, we're not doing any periodic boundary conditions in a sense. Now I could spend the remaining time, actually if you don't turn it towards me, I have no idea what the clock tries to tell me. No, if you want me to check the time from time to time, you should turn it. So I'm not going to show you 10 slides of equations. You can find them in these papers and in the supplementary materials. I'm going to present you some experimental verification of that using a chain of transmon qubits. This experiment was done by the group of Dian Tan at Shenzhen. If I remember well, Dian was Cater's first PhD student in St. Louis, so the world is rather small. And that's the experimental system. And we use different number, a chain with a varying number of qubits, 5, 8, and 11. But this is a schematic. The only thing you really have to know is what is seen in this plot. So we have a chain of 5 spins, for instance. We apply noise in the middle. And if we want to play with the system a little bit, we can even detune them. But I come back to that in a second. So actually, this is the smallest possible chain that satisfies this synchronization condition that I presented on the previous slide. 5, n is equal to 5, and u, in the middle spin, u is equal to 3, where the Gaussian white noise is applied. What are the experimental results? These are the first ones. So you see the mean, or the expectation value of the sigma z component of the spins. The first plot shows you 1 and 5, so these are the 2 n spins. What you see in the background is if you don't apply any noise, so this is unitary, almost unitary evolution, you see each spin does oscillations, but clearly it does not synchronize. And then you apply this Gaussian white noise at the middle spin, and then you realize that after a while, the 2 spins start oscillate in sync, like my metronomes, but now in a quantum system. You could do the same with 2 spins 2 and 4, so that the ones closer to the middle, and exactly the same happens. If you don't apply any noise, they just unitarily evolve in time, no synchronization, and if you apply the noise, they start synchronizing. So the edge spins, if you think about quantum communication applications, the edge spins, the end spins, edge spins are synchronized. The interesting remark here is that the period is set by the coupling strength and not by the frequencies of the individual spins. So that's a nice remark here. So now what happens if you do not fulfill this synchronization condition? So you don't apply the noise in the middle, but to the first spin, for instance, nothing. So everything decays to 0, or decays to no oscillations, there is no synchronization in that case. 5 was the smallest chain. We can take a larger chain, n is equal to 8. The condition, synchronization condition, is still fulfilled if you continue applying the noise at spin number 3, which is not the middle spin anymore in that configuration. What you see here is spin 1 and spin 7. After a while, they're going to be synchronized. The same is true for 2, 4, 6, and 8. So the entire chain is actually synchronized. The interesting thing, if you look at the end spins, 1 and 8, they're not going to be synchronized, but anti-synchronized. So you can actually, by playing with the system and where you apply the noise, get whatever you want to have. Synchronization, anti-synchronization, and things like that. I told you before that in the quantum regime, it's very difficult to quantify if we have synchronized oscillations or not. So we need a measure. I mean, looking at plots is nice, but we want a number. And what people very often use is the classical Pearson correlation coefficient, which measures the correlated. It's basically the normalized covariance between the two expectation values of two spins. And it just tells you how strongly these two spins are correlated. So as a function of time, you start with actually no correlations. And as a function of time, this Pearson coefficient achieves the largest value that you can reach, 1. It's perfect correlation. And the small red arrow here shows you where the Pearson coefficient becomes larger than 90%, larger than 0.9, and we define this as the onset of the synchronized phase. And this is true for 1,5 and 2,4. So these spins are maximally correlated in the classical sense, right? They just do this, like the metronomes at the beginning. Now let me tell you a few words about the synchronization mechanism. Because noise-induced synchronization is one form of classical synchronization. The question we might ask now is, what are the ingredients that need to be there to have synchronization in a quantum many-body system? And actually, you need two things. The first one is you do need some dissipation. If you don't have dissipation, you're going to have all the modes oscillating freely. Unitary time evolution, there's no way they can synchronize. So that's a big difference between classical and quantum. In quantum, you do need noise, a noise source. You do need dissipation. If you don't have that, you cannot have synchronization. And this is actually the frequency spectrum of the 5 spins measured in the experiment. Without the noise, no synchronization, you see that each spin has its own frequency. You apply the noise, all the modes decay except one. Meaning there's only all the spins oscillate at the same frequency. Yes?
It's not clear to me. Are you using the word dissipation and noise interchange?
I need a decay. I need an eigenvalue with an imaginary value. No, in that case, the noise does it. I need some dephasing. Right. I need some non-unitary time evolution. So the criterion is, I mean, if you're looking at a master equation, you need a Liouvillean. You look at the spectrum. You need one. I mean, they should all lead to a decay except one which has a 0 imaginary part. So you need imaginary parts for all of them, decay, and then.
But there doesn't have to be any loss.
No, dephasing. You just need to suppress the oscillations you don't want to have.
Yeah.
So the second ingredient you need is having one oscillating mode is not enough. You want stable. I mean, having transient synchronization is easy, but you want something that continues oscillating for almost ever. And then the second ingredient is we need some decoherence-free subspace, meaning a subspace of your Hilbert space that is actually decoupled from the environment. Once you land in that subspace, in the ideal case, you're fine because you're completely isolated. And this leads to unitary stable oscillations. So these conditions, this synchronization condition I showed you a few slides ago, this n is blah, 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 u is equal to blah, blah, blah. This is the condition behind. This is what we were looking for by using the exact solution of this XY spin chain. Now you might wonder, what's the difference between classical synchronization? What's the difference between quantum synchronization? Adolfo. On the previous one.
Before you get into that, is the noise you are adding classical noise, is local or global?
In that case, global. We just apply it to one spin. You can do 2, you can do 3. Actually, I'm skipping all the details. I mean, if you look at the supplemental material of the PL, we have actually, it's the same effect just with a renormalization of factor 2 if you apply at 2 slides. But we apply it at one side. That's easy, right? It's much easier experimentally. You have a chain. At one point, you apply some noise. and then you synchronize the entire chain, which is not completely obvious, right? Because the chain can be long, and you apply the noise only at one. So coming back to the what is quantum? Go ahead. This one? No, but the three actually, the one in the middle is not going to do anything. So if you're in a synchronized, so these two are going to be synchronized, these two are synchronized, and because of the symmetry, the one in the middle can only be synchronized with itself, so it doesn't do anything, it stops oscillating. Actually, I think you see it, no, you see it here. That's the one in the middle, the gray line there. Because of the symmetry, it cannot, I mean, the poor guy is completely alone. That's the one not doing anything. Actually, it stops oscillating. It's kind of a frozen state, if you wish. So what is quantum in quantum synchronization? And so we looked at the concurrence, so a measure of entanglement between the two end spins. That's measured data plus theory. And as you see, the two are entangled. So you have two end spins of a spin chain that start oscillating in sync, and on top they are entangled. So you have stronger than classical synchronized oscillations. And this is the very first experimental observation of that. It's stronger than classically possible. The correlations are stronger than classically possible, right? So we're far from a Bell state, but the concurrence is different from zero. And this makes a big difference, because if you, again, think about potential applications for quantum communication, now we have a chain and we are able to synchronize them, and at the same time, they are stronger than classically correlated. You remember the tongue I showed you on one of my very first slides? Let's come back to that now, but in the experiment. And I'm going to look at two Arnold tongues. The first one for the synchronization part, meaning I'm going to look at the Arnold tongue for this Pearson correlation coefficient, and at the bottom I'm going to do the same for the entanglement. The big question here, and all the theory we did was for a perfectly ideal chain. So all the spins had the same frequency, they were completely identical, everything was ideal. No experiment is ideal. So the question is, does it survive, does it occur, and how stable is it, how robust is it? So what you see here is the measured Arnold tongue when we vary the detuning between the two end spins and we vary the strength of the noise. And what you see here is not too surprising. The first thing is if the detuning is small, actually if there's no detuning, that's the best condition for having very good synchronization between the two spins. Fine, that's what you would expect even classically. The thing that you also notice is by increasing the noise, it gets better. Which again, is not too surprising because it's noise induced. The more noise you have, the better the synchronization. That's what you would expect. And this is actually what we see in the experiment for the Pearson correlation coefficient. And then we do exactly the same now for the entanglement. So what you see here is the concurrence as a function of the detuning and the noise strength. The first reassuring thing is, again, if the detuning is small, it's easier to entangle two end spins, fine. But now if you add the noise, actually the concurrence goes down. Is that surprising? No, of course not. Right? Noise is bad for quantum mechanics. So the more noise you have, the less quantumness, the less entanglement you expect. So you have this sweet spot between having lots of noise to have a good synchronized state, but not too much, because if you have too much, you kill the entanglement part. So yeah, there's a sweet spot in the middle. And if you have that, you have stable, so the first message here, it's robust, right? So even though the experiment is not ideal, we have, for a large parameter regime, we have synchronized oscillations, and they are even entangled. So quantum synchronization is stable. That's the message. The message here, and that's the end of the second part of my talk. There were no trajectories so far, so you might be wondering, will they come one day? They come now. So I'm going to replace the classical noise source by a source of quantum noise, meaning I'm going to try to verify if there's measurement-induced quantum synchronization. So the system is just the same. I take my spin chain, but instead of applying classical Gaussian white noise on one of the spins, I'm going to measure it. I'm going to do homodide measurement. Why not? So that's I have to show you one stochastic master equation. That's the one we saw many times in the last days. And I'm going to measure one spin, Z, sigma Z, component of that spin at a single site U. And the question I'm going to ask is, can we have synchronization along single trajectories. And again, I could show you 10 slides of calculations. I'm going to do none of that. I'm just going to show you a few plots. But for concretely, you're going to have a chain of 8 spins. Again, we measure spin number 3. And if you look at the structure of the Hilbert space in that case, you're going to realize, I can tell you there are 2 decoherence-free subspaces and 1 complement, which is not a decoherence-free subspace. And I'm going to call Q1 squared the probability to be in the first, Q2 squared the probability to be in the second decoherence-free subspace, and the P squared is just whatever, the remaining part of the Hilbert space. So I'm going to consider 3 different cases, one after the other. And let's start with the first case, where the initial state has an overlap, initial probability of being in the first decoherence-free subspace of 2/5, 0 for the second decoherence-free subspace, and the remaining part 3/5 in the complement. And what you see here are the expectation values of the n spins, the first and the 8th one, but along trajectories. So it's for one trajectory. Are they synchronized or not? I think it's interesting to start by looking at this subplot here. So the trajectory, the system is going to do whatever in the Hilbert space, and at some point it's going to hit, by chance, the decoherence-free subspace, and then it's going to stay there forever, because it's going to be isolated from the rest, it's going to be unitary. And this happens when you see this small red arrow here. And before that, there is no synchronization. And once the system enters and stays forever in the decoherence-free subspace, we have synchronized oscillations along one single trajectory. In the case where you end up in the complement, with probability 1, nothing happens. The trajectories continue to fluctuate as if nothing had happened. So no synchronization. In that case, no synchronization. In this case, along trajectories. And then you might ask, what happens if I know average over everything? What happens at the Lindblad level? You have nice synchronization. So here we have a situation where we have synchronization along single trajectories and at the level of the ensemble. And what I can tell you is the number of trajectories that end up, that number of trajectories being synchronized is given by the overlap, the initial overlap with the decoherence-free subspace. And there's a nice way to calculate that, but I'm not going to go into that. But the nice thing, again, to re-emphasize that, is a spontaneous transition to a synchronized state, synchronized phase, if you wish. It's not a phase transition, we check that, but it's a spontaneous transition. You monitor, 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 and boom, suddenly you are synchronized. Second case, I'm going to play some quantum tricks. I'm going to take an initial state which is in a superposition of decoherence-free subspace 1 and decoherence-free subspace 2. So it's 1/2, 1/2, and nothing at the complement. So the system has a probability of 1/2 to end up in one of the decoherence-free subspace and be synchronized. So there's some wiggling at the beginning, and once it's in there, boom, it's synchronized. The same happens if the system ends up after some noisy trajectories in the second decoherence-free subspace. It's nicely synchronized. It's more or less the same message as before. As soon as the system enters one of the decoherence-free subspaces, it gets synchronized along single trajectories. But now you take the ensemble average over everything. And it's not an accident that which was 1/2, 1/2. Because in that case, you have destructive interference, and there's absolutely nothing at the ensemble level. So if you only know the Lindblad master equation, you look at it, no synchronization whatsoever. You need to open the box and look at the trajectories and realize there is actually, along all trajectories, because half of them end up in that state and the other half in that state. So all the trajectories show synchronization. You take the average, it's gone. So what we learn here is that the knowledge of the ensemble average is not enough. And then I can ask Eli, what do you expect in that case? Non-ergodic.
The time is moving.
We have more than 6 minutes. I have 6 minutes. I can allow myself to ask you a question. It smells like non-ergodicity. So the ensemble doesn't, okay, fine. So we looked at ergodicity. So the measure of ergodicity, ergodicity in the Boltzmann sense, you take the time average, take the ensemble average, and if they're equal in the long time limit, you're ergodic. So to verify that, we took the fidelity between the time average and the ensemble average of rho of t, and then we took the average over the noise. And that's what you see plotted as a function of the initial overlap with the first decoherence-free subspace. And then you realize that in most of the cases, it's not ergodic, because it's not one. They're not identical in the long time limit, unless the system starts in one of the decoherence-free subspaces, which is not too surprising. If you start already in one of the decoherence-free subspaces, you're going to live there forever if you take the average or not. It's just giving the same. The interesting thing is, if you jump now to my first part, no, second part, the noise, the classical noise induced, you can do exactly the same calculation, and then you realize it's always ergodic. So the classical noise-induced quantum synchronization is always ergodic, the dynamics. The quantum, the measurement-induced, is not. So it's very different. And what you see here is trajectories for the noise-induced case. In the classical noise-induced case, there's no synchronization whatsoever. But I told you in the second part of my talk, there is at the classical level. They did the experiment. So not think just for 1 second about that. I had one case where all the trajectories are synchronized, the ensemble average is not. And I have just the opposite. The ensemble average is synchronized, shows synchronization between two end spins. There's not a single trajectory that is synchronized. And I let you think about that. I'm not going to give you the clue. It's slightly mind-boggling. Once you know the answer, it's trivial. In hindsight, everything is trivial. But it's just the opposite. You look at all the trajectories. None of them show synchronization between the two end spins. You take the average, bah, there is synchronization. The last case is we take another longer chain, n is equal to 9. We apply now, we measure spin number 5. Now the structure is way more complicated because we have two decoherence-free subspaces. They have dimension 8, and there are 4 different eigenfrequencies. But what I told you before, now you can play quantum tricks in the sense that you can do the classically, but I can prepare coherent superposition of states for my initial state. And by doing that, you can actually choose the synchronization frequency. So that's one example where the system ends up in the first decoherence-free subspace with frequency lambda 1, and frequency lambda 1 is just J, the coupling constant between my two spins. If you take a different linear superposition, you end up in a different decoherence-free subspace, this time with frequency lambda 2, and lambda 2 is square root of 5 times J, so everything can be calculated analytically. The third example is a synchronization frequency of square root of 5 plus 1, and I didn't show you the last one, which would be here, but what you have here is that by choosing an initial state, which is a linear superposition of different different overlaps with decoherence-free subspaces with different frequencies, you can actually have synchronization along single trajectories with different synchronization frequencies for each trajectory. So in a sense, it's a kind of quantum form of multiplexing. You have one trajectory synchronized with one frequency, the other one with another frequency, and if you invest the time and the energy, you can do whatever you want to have. So this really emphasizes the role of coherent superpositions of states for quantum synchronization, and this makes it completely different from my kind of boring but nice-looking metronomes that I showed you on my third slide. And that's already the end. I have 1 minute and 45 minutes. No, seconds, sorry. No, but, okay. I told you many things, but I would like you to remember 3. The first one is that classical synchronization is almost everywhere and important, also for technological applications. The very reason why you are alive is because your heart cells oscillate in sync. Think about that for a second. Once they start losing the synchronization, you die. So you are alive because of classical synchronization. Quantum synchronization exists. It's very different from the classical one in the sense that it has to be noise-induced, in the sense that it can show entanglement, and it's an emergent field. And that measurement-induced synchronization shares many properties of the noise-induced, but it's different. The main difference is it's non-ergodic. So you can have a single trajectory is no longer representative for the ensemble. Let's put it that way. And if you want to have all the technical details about the calculations, these are the references. The last one is the experiment. Thank you very much for your attention.
Thank you very much.
Yeah, beautiful talk. I'd like to consider the role of coherent superposition. So if you if you initialize in
So I take an initial state.
if you initialize with a density matrix, which is not a superposition, but let's say you start with a half probability to be in the first decoherence-free subspace and half probability to be in the second one. Don't you see?
So the probability to end up in one of them at the very end is given by the initial overlap. That's the interesting thing.
Yeah, but I'm saying, so here you started with superposition. No, not in this one, but maybe if you can go. Yeah, for instance, this one. So here you start with a coherent superposition of both. If instead you start from a mixed state, which is either 1 or 2, but not a superposition.
So you want to do a classical mixture.
Yes. Would that work as well?
Is what happens here.
So you wouldn't see the.
I mean, it will still end up in one of the two because the overlap is unaffected. This one is, you're not going to have the interference part of it.
Yes.
So it's still going to end up in one of the two decoherence-free subsets, but the average is going to be different. And actually, I'm not even sure if we have a plot for that, but you lose the interference part.
I see. Okay. Thanks.
Yeah, intriguing talk. Could you go back to your...
Less intriguing than yours.
Sorry?
Less intriguing than yours.
Could you go back to your definition, the quantitative measure with the covariance? With the covariant, this one, yes. So you have a covariance of quantum averages here. Yeah. So this only makes sense if you're averaging over something which is not quantum.
Yeah.
So it has to. So it seems to me this is only defined for individual trajectories. So what does it even mean when you talk about synchronization from the Lindblad equation?
Well, this one is actually for the Lindblad level. So we calculate the expectation values, and then we check if they are equal or not in a long time limit. What I didn't.
But wait. But if it's the Lindblad solution, then it has a deterministic solution, and so there's zero covariance. Would always be zero.
No, not if you apply the noise.
No, but that's what I'm saying, that this only makes sense if the covariance and the variance is over some other sort of random.
Which
I can see that this makes sense at the level of individual trajectory.
Actually, you need to adapt, you need to generalize that to be still valid at the level of trajectories, which is something I did not mention at all. So I didn't tell you the entire truth, just part of it. But this one.
So I don't understand how that can make any sense at all.
Can we discuss it afterwards? Because there's one thing that you miss, and I'm not sure if I can identify it. Because these are deterministic, right? Because you don't see any oscillations here. These are expectation values.
What's the covariance? What are you averaging over to get a covariance?
Over the noise.
But they're saying if you have the Lindblad, there is no noise in it.
No, I apply classical noise from outside.
I know, but you could describe that part of that equation.
Sure, which we do. But
then everything is deterministic.
No, but it makes a difference if you apply the noise or not. It's not the same time evolution.
Of course not, but the Lindblad description is deterministic.
Yeah. Can we discuss it afterwards?
I suggest you continue discussion later.
That's what I think we agree on that.
I have a question. Oh, sorry.
Sorry, just a quick question, Eric. So this point about having some sort of noise plus some sort of decoherence-free subspace, this joint point, to me it seems like you're asking for Lindbladians with strong symmetries, because you want to have multiple steady states, and if and also you want oscillations. So you want to be on the imaginary the real zero axis of the Liouvillean superoperator, and you also want basically multiple steady states. Do you agree to that? Do I understand this right? Because
I would say yes. But
this is our perspective on what CTCs should be, actually. And so, this was the conversation.
There's a connection to that. Actually, since Gonzalo is in the room, I should mention that they had identified the role of the decoherence-free subspace already before that for transient things. But I would say yes, but I would invite you to continue discussion afterwards before you leave. Right?
Yes, yes, very much. And just one last question: the Hamiltonian synchronization with the noise, how stable is it to energy pumping? So is it stable to initial conditions? It doesn't matter where you start.
Yeah. When actually we even did an experiment with a randomly chosen initial state.
Okay.
So the data that you show is the one is in the excited state, all the others are in the ground state. But then we just choose a random state. And as long as these conditions are satisfied, it does not depend at all on the initial state, which is actually kind of, it would be very bad if you had to choose a very specific initial state. So take a random one that satisfies all the conditions I have, boom, it works.
And the stable synchronization condition is it exactly the
same one?
I'm just trying to check my intuition.
It's independent or it does not depend on initial
when
state.
you derived it, is it, I mean, so you mentioned that you use some formal techniques like Jordan Wigner, but is the intuition that you again are just seeking for, if I generically choose some random and then try to write the effective Lindblad, I imagine that it has just a zero steady state, like which is unital map or something. It'll just go to something which is either the temperature, which is defined by the noise spectrum or something like that. For you to get a very specific oscillation, I would imagine that you need to kind of fine tune, which is what the condition seems to be here. But that I want to understand if the fine tuning is multiple steady states.
You need to pick up one mode, which is going to be the synchronized mode. But I'm the only one standing between these guys and lunch, and I fear for my life. So can we discuss afterwards?
Absolutely.
So
yes,
that we can.
I join you. Yes, right afterwards.
Thanks.
Okay. Let us synchronize our stomach and the lunchtime. Thank you very much, Eric. Let's thank the speaker again.